Hi everyone, and welcome back to another LeetCode problem. This one was also on the last LeetCode contest, and this one, along with the other one I did, were worth the most points. So in this problem, we're given a matrix, and we can start at any index in the first column, and we can iterate either to the right, or diagonally up, or diagonally down. So like from this 2, we can go here, or this is out of bounds. And the other condition is the numbers we iterate to have to be strictly increasing. So we can't go like 2 to 4 to 3. So if we start at 2, we can go 2 to 4 to 9 to 11 would be one path. We can go 2 to this 4 to 9 to 11 would be another path. That's all we can go from here, and then from this 5 we can't go anywhere because we have to be going to the right, and these are all smaller. From this 3 we can go 3 to 4 to 9, then we're stuck. 3 to 4 to 9 as well, and then we're stuck. Or we can also go down 3 to 4 to 13, then we can also go 3 to 9 to 13. And so from looking at this, so if I draw this really fast, or I don't even need to draw it, but we can see that we are doing a lot of repeated work. So for example, if we go from 3 to 4 to 13, or we go 3 to 9 to 13, we hit this 13 multiple times. And that can happen a lot, so we can hit the same value multiple times. And when that's the case, you're going to want to have some kind of visited array, or some kind of visited hash map, to make sure, was I here already? And also, we can keep in mind, how many moves can we make from once we get to a point doesn't impact where we got there from, because we're always moving to the right. So if we got to this 13 from here, or from here, or from here, from anywhere, the amount of moves we can make once we get to this point is the same. So this is going to be a fairly straightforward algorithm, and it's going to be a dynamic programming algorithm. And so how would we do this? Well, we would say dp of whatever index is, if we try to move every single direction, and then whichever direction we can move, so we would add, like let's say we can move here. So dp of this would be 1 plus dp of this, because we made a move. So we went from here, we 1. And so we can try to move in all 3 possible directions, so we'd have to check, are these 3 locations able to move to? Do we already have any of these values? And if yes, then we just take the maximum of whichever one, and we have the hash map so we don't do the repeated work. So let's code this up and see if we run into any issues. This is going to be a pretty straightforward one. So first of all, we have the visited set as usual, or the visited dictionary. And then I think I did this in some other problems, but for any of these problems that have this kind of matrix, I like to have a rows and columns, because we're usually going to be doing some kind of looping, and we're going to be comparing, are we out of bounds? So I like to make these, so we don't have to do length grid and length grid 0 and things later on. Okay. And that's all that we're going to need for this problem. So now let's make our dp. And we're going to have a row and a column here. And so normally when I do these dp algorithms, I like to have out of bounds conditions. But in this case, because we're starting at a valid index, and I'm going to manually check, can we go to the next one? We're never going to be out of bounds because we're going to be checking for that inside the actual dp algorithm. So the only thing we need to check for is, did we hit the last column? So that's the other thing. If we're on the last column, then we can't go anywhere else and we're stuck, and we can just return 0 because we can't make any more moves. So and then the other thing we do need to check for is if we've already been here before. So pretty standard. Okay. And so now what we need to do is we need to check every single location that we can go to. So we can just have some res variable, make it 0. Now we need to see, can we go up? So in order to go up, we'd have to say if row. So to go up, it has to be, the row has to be greater than 0. And now we also need to check if this value So this would be this case, row minus 1 column plus 1, which would be up here. So row minus 1 column. And it has to be strictly greater. So then we can just take whatever the max is of res and dp of row minus 1 column. And then remember, we do have to add 1 because we made a move here. So we can just actually copy this, and we're going to have 3 of these for every single location. We can either go, remember, up, forward, or down. And so when we go forward, we don't have to have this row check. It would just be, oh, by the way, I forgot one other thing actually. So this should be column plus 1. And this should be row column plus 1. Just space that a little. Okay, and then this is just this. And now here, we need to see if we can go down. So in order for it to go to down, row has to be less than rows minus 1, because rows minus 1 is the final row. So if we're at rows minus 1, then we would go out of bounds. And so this is plus 1, I believe. Yes. Recipe. This. Oh, and I forgot these as well. Okay, then we just make this visited row column equal to our result, which is normal for DFS and DP. Okay, and we just return here. And so now what we need to do is, because we can start at every column, we need to compare every single one of these. And so what we're going to do is we're going to have a res outside here equal to 0, because the least number of moves we can make is 0. And then at every iteration, we can just take the max of the res and what we got. So we can do something like this. Row in range. Rows, we're going to be going through every row in column 0. So res equals max res dp row and column 0. I'm going to return res here. Okay, let's try that. Okay, invalid syntax. Oh, right, so like I said, we don't need this and situation. That does kind of fast, so hopefully it didn't make too many mistakes. Okay, cool. Alright, so let's think about that time and space complexity here. So for time, what's the most locations we're ever going to visit? So we're never revisiting a location. That means our time is going to be, let's say this is an m by n matrix, the most we can ever visit technically. So every iteration we're going all the way to the right, and we can visit every, if we start at every column, we can technically visit every square, but we're never visiting any square twice because we are checking for that. Or we are visiting it twice, but if we visit something twice, we just return right away, so it's basically 0 time complexity here. Okay, so I think the time complexity here would be m by n, which is pretty common for DP or DFS when we have a visited set, or a hash map. And then space, so we have this visited, and this can technically have every single square. And so in that case, it would be m by n as well. Okay, so I hope you guys like this problem, and if I made any errors, once again, this is a new problem, there's no tutorial, so let me know in the comments, and I'll see you in the next one.